All right. So we were looking at the partial differential equations and the use of the methodology of separation of variables. And the first example we saw was where we had values of the dependent variable given on the two sides, and the boundary conditions were homogeneous, and we were able to use the Fourier series and say that I can get some kind of a summation solution. Now then we took the same geometry, except that the left side was having some kind of a constant value given, and at x equal to L, the gradient was given, and that meant that there was a non-homogeneity in the boundary conditions, and we need to go ahead and make them homogeneous so that the solution methodology is going to be applicable to us. And there are several ways in which one can do it, and in this particular situation we said that we're going to change the variable and introduce a new variable which is u minus u0. The right hand side also has a u minus u0 for the sake of convenience, and we'll relax these things as we go along. But as of now, let us just say that the u0 is the same on the left side and right side. And when we change the variable to u minus u0 equal to theta, we are ending up with a system which has got homogeneous boundary conditions. So it's a linear differential equation with homogeneous boundary conditions, and we use the same methodology, which is to say that theta is going to be a product of f and t. G, f is a function of x only, g is a function of t only, and we did a little bit of algebra, and this time we argued that the value of lambda, which can be either 0 or positive or negative, can be approached by looking at the x equation. The previous case we had argued by looking at the t term, so both of them should give us the same values or the same conclusions, and this was a little bit more algebra intense, but we did that. And finally what we said was that the only possibility is where you are going to get sines and cosines as the solution, and f is going to be a cos kx plus b sin kx, f0 equal to 0, and on the right hand side the gradient of f has been specified. The gradient of f being specified ends up in some kind of equation, and that has got this so-called eigenvalue sitting in here, and we need to try to get a solution for that equation. And the classical way is to go ahead and equate these two to a y, make a plot, and see where the two lines are intersecting, and those are going to give you the solution to that transcendental equation. Nowadays you can just go ahead and use any of these standard available codes which are going to be giving you this fairly straightforwardly. But the more worrisome part in here is that we can go ahead and make the same approximation of the fact that we have a linear differential equation. So the sum of the solutions is going to be a solution, and the other conditions are anyway getting satisfied, but then the last condition, which is the so-called initial condition or the condition at t equal to 0 gives you some trouble, and that means that Px is going to be equal to the summation, and the standard methodology is to go ahead and try to think about these eigenfunctions as being orthogonal functions. And if they are orthogonal functions, then you can, assuming the functions are orthogonal in this particular case, although we have not shown it yet, but these sines and cosines are orthogonal only if that n is an integer, and in this particular case, the k is not necessarily an integer, and therefore sin k nx and sin k mx are not necessarily orthogonal. And that means that you don't have any business to do this right away, but we have done it anyway. We said we are going to see why we are going to be doing it. That's why it's kept in red as of now. So km and kn are not integers. So the trigonometric functions being orthogonal does not hold anymore. But if we assume that they are orthogonal, then you can go ahead and do the algebra, and you're going to get the coefficients. Okay. And once again, I put these in red here because so far we have not shown that they are going to be orthogonal, and we need to show that. Okay. Otherwise, we have no business to say such things. Okay. So this works only if the or because the eigenfunctions are orthogonal and the differential equation is in the Sturm-Liouville form. So we see now what is the so-called Sturm-Liouville form, and there is something called a self-adjoint operator, and this is a definition that we will use again. So this is a self-adjoint operator, and the self-adjoint operator is one which is going to be amenable to this type of an operation. Okay. So it's a linear operator again. So L, if we have got two functions, let us say f and g, L operating on f and then g, the inner product of these two is going to be L operating on g and then f. So this guy then qualifies to be a self-adjoint operator. The math guys are much more there. I have used in the definition, I have used g prime, but then we are going to be interested only in real functions, and therefore g bar is going to be equal to g. G bar is the complex conjugate. If we are talking about complex functions, we are not going to be talking about complex functions here. Okay, so might as well just go ahead and say it is going to be a real function. Okay, so the inner product of f and g we had said was integral of fg. So this was our definition, and again we keep tweaking the definition here and there, so that we will do here also, but in general the structure remains more or less the same. Once again, the math guys do this much more rigorously. We are waving our hands quite a bit in all of this. Okay, now what also happens is that a operator which is self-adjoint under certain conditions is not necessarily self-adjoint under other conditions. Okay, this is something also that we need to appreciate here. So I've taken just an example. The linear operator is d square dx square. We know this is a linear operator, and there are these conditions also. Fa is equal to 0 and FB is equal to, let us say, 0. Okay, so FA is equal to 0, FB equal to 0, GA equal to 0 and GB equal to 0. Remember that these so-called boundary conditions also have to be given to us. When we talked about the inner product, when we were looking at 2 pi periodic functions, we never explicitly said this for the simple reason that we qualified these functions as being 2 pi periodic, which means that y at 0 is equal to y at L and y prime at 0 equal to y prime at L was understood in there. Whereas here we are just saying a and b are two limits of that function. So the function is existing, or all this business is going to be valid in the range between a and b. Okay. So d square f d x square, this is a linear operator. So what we say is, let us just apply the definition, which is integral of, now this is d square dx square f times g. If this guy is equal to d square g dx square times f, then it qualifies to be a self-adjoint operator. Okay, so that's what we are saying. So this guy is self-adjoint, but then we have put our conditions also, which is fa equal to 0, ga equal to 0, fb equal to 0, and gb equal to 0. So now we just do some brute force algebra, just integration by parts. So we say that I take this guy and then I integrate this guy by parts. So I've got my first function, integral of the second, a to b minus integral of the second into differential of the first, okay, between a and b. And if you do this, you will get f g prime between a and b minus integral of f prime g prime dx. Okay. So if this condition is going to be satisfied, then this operator which we have used, d square x dx square, is going to be a linear operator. My apologies, a self-adjoint operator. Okay. Now let's just open this guy up. So I can open this bracket, and this guy is equal to this guy, right? There's no question about that. So I can throw this out. So this is equal. So this is fine. I've got gf prime. So this guy is g times b, f prime b minus ga f prime a must be equal to f b g prime of b minus f a g prime of a. If this is satisfied, then this guy which we have identified as some kind of a linear operator is indeed going to be self-adjoint. Okay. Now the conditions are there. Fa is equal to 0, Fb is equal to 0. So this term is gone, this term is gone, and Ga equal to 0 and Gb equal to 0. So indeed this is self-adjoint under the condition that Fa equal to 0, Fb equal to 0, Ga equal to 0, Gb equal to 0. Okay. Now let us take one more condition which says Fa equal to Fb equal to 0, but Ga is equal to Gb, it's not equal to 0. Okay. So Fa equal to Fb equal to 0, so this term is gone, right? But Ga is equal to Gb is all that we are saying. So which means that I'm going to have this guy like so. Okay, this is equal to 0. And with the given information, there's no guarantee that that's going to be that. Okay, so the same operator which we are seeing, d square f dx square, is self-adjoint under some conditions and not self-adjoint under other conditions. Okay, all that I'm trying to emphasize here is that whenever we are trying to say something is self-adjoint or not, at least within the framework of what we are talking about, we need to have the boundary conditions also properly in place. Okay. So now we look at the so-called Sturm-Liouville system, and this is d dx of p y prime and plus some q which is a function of x, this p is a function of x, y is equal to w which is a function of x times, so this is an eigenvalue problem. Lambda is the eigenvalue and we have got minus d dx of p of x, and then you are having a y prime in there. Okay, so if you will, you can just even say that this is d dx and this whole thing is my operator, right? So this is that linear operator that I'm talking about. So this is my linear operator L that we have been talking about, which was d square x dx square in that particular case. Okay. So for the Sturm-Liouville system, we are also going to now put these conditions which are homogeneous conditions. So alpha 1 ya plus alpha 2 y prime of a is going to be equal to 0, and beta 1, so these are the two end conditions, and we will write alpha square plus alpha square equal to 0 so that you don't have zeros in there. Okay, so that's the only purpose of the alpha 1 square plus alpha 2 square equal to 0. Okay, so if both of these are 0, then that condition itself goes away, which means the condition is not existing, and therefore we put that rider which says alpha 1 square plus alpha 2 square equal to 0, beta 1 square plus beta 2 square equal to 0. Nothing more than that. So I'll not explicitly write that. So here is my system, and we will write this slightly differently, and we'll put this w which is called the weight function. So this is an eigenvalue problem, and if this is a self-adjoint operator, again this comes from math, we are not going to prove anything in this particular course. If this guy is a self-adjoint operator, then there are infinitely many real distinct eigenvalues. Okay, so this is something that we are not going to try to prove this theorem, we are just going to take, that's all. Okay. The eigenfunctions are orthogonal and they are a set of basis functions and orthogonal with respect to this weight function w. Okay. Now what was our condition, or at least we had said in the past that if you have two orthogonal functions, the inner product is equal to 0. That's all we said. Okay. Now, what has orthogonality do with this 90-degree business as far as functions are concerned? We said let us not worry about it. Don't try to visualize any of this. When we had vectors, they were 90 degrees, we could visualize it. But when we are talking about functions, this is my definition of orthogonal functions. This is equal to 0. And my inner product definition is slightly different than what we had. There is a weight function also that comes inside. Okay, so there is a weight function. So inner product of F and G now is F, G, W. Okay, where W is that W there. So that's my weighting function. Okay, these are definitions that we are using so that once you have these consistent set of definitions, you then move ahead and say that I can't change the definition anymore. So that's what the function is all about. Okay, all right. So the Sturm-Liouville system is one where if that is, and we'll show that it is a self-adjoint operator, we'll just demonstrate, we'll not prove anything. There are infinitely many real distinct eigenvalues and the eigenfunctions are orthogonal and they form a set of basis functions and they are orthogonal with respect to W. And we are defining the inner product as this. So when we say they are orthogonal, it means that this guy is equal to 0. Okay. So once again, I want to emphasize that fact that you're talking about an operator, but then when you're talking about the operator, you are talking also about the conditions at the extremes because you are having a definite integral. So this A and B are important. Okay, so that's why I'm keeping on writing it so many times. The demonstration is a little bit algebra intense, so we are going to attempt to do something and try to show that they are self-adjoint. Okay. So that's my linear operator that I'm talking about. And the inner product now of L and G, this is going to be, the inner product now has that weight function in the definition. Okay. So I've got L times G, L of F times G. So I've got 1 by W, right? Then minus of P times F prime, the whole prime. That's what the first term is going to be. Plus, there is going to be a Q times F, right? So this guy now is going to be the inner product of the operator operating on F times the function G. So 1 by W minus of d dx. So I'm just putting that as a differential sign here in this d dx and plus QF. Okay. So this is equal to inner product of the linear operator comma F. Okay. So LFG LGF. So we'll open this guy up and then write the other thing. So this guy, if I open this guy up, I'm going to have, and this has got W times dx. Okay. So this W goes away. This W is gone. Okay. So what we now are saying is that I have got this function here and I'm going to now go ahead and open up the brackets to the extent possible. Okay. So I've got this guy here and this is d dx p df dx plus qf and there is a g sitting in there. Okay. So the first function, which is p f prime times the integral of the second. So this is one of these functions. So g times the integral of this, g times p of f prime. This is a, this is b. That's one of my terms, minus of integral of the second, which is this, differential of the first, which is that, plus integral of q f g. Okay. So I've just opened this guy up, nothing else I have done. Now, if I look at this term here, now let us look at this guy here. Don't want to write the whole thing down, but this term here is going to be the same. Q, F, G is going to remain the same, right? Similarly, P, F prime, G prime is going to remain the same. So both sides are going to have this term and this term. So all that we need to now do is to say that this term has to be the same. Okay, I'm not doing all the algebra there, but all the algebra is there. So what we are saying is I've got a linear operator which is L operating on F comma G, that's the inner product of these two, and I'm just doing brute force algebra. So when I'm doing brute force algebra, one of the terms is this term here, and I have got two other terms here. So I've got a term in blue, a term in green, and a term in black there. Okay, and the next fellow, if I'm going to open up the brackets just like I have done here, again I have got a term in blue, I have got a term in green, I have got a term in black there. Okay, and what you see is this term and this term here are the same on the left hand side and on the right hand side. Okay, so the colored terms there, integral of QFG, integral of PG prime F prime, are the same for both the situations, which is for LF of G and for LG of F, which means that I can cancel them out. Okay, so I'm not writing the whole thing, but I think you will appreciate now that the expression 1 must be equal to the expression 2 if this is a self-adjoint operation. Still, of course, we have not yet put the boundary conditions. You do that. The only thing, therefore, you have to show is that this guy is equal to Gp times G prime times F. Okay. So this operation, which is LFG is equal to LGF, do all the algebra and two terms from each side are going to cancel off, and all that you're going to be left with is P F prime G equal to P G prime F. P is the same, so we are going to say that if I'm going to be able to show that F prime G AB is equal to G prime F, again AB, then I'm in good shape. So that's basically what we are doing. Just brute force algebra is happening, nothing else. Okay. So P G F prime A to B must be equal to G prime P F A to B. How do I show that? I need to look at my conditions here. Okay. So I need to look at my conditions. So F prime of B. What is F prime of B now? What is F prime of B? Looking at the conditions here. F, this, what is the parallel between F and Y? F and Y are they the same? F and Y are the same, right? G and Y are the same, right? So all that I'm saying is these are some dummies that we have taken. Okay, so F is some dummy function, G is some dummy function, that's going to satisfy that anyway, right? So F prime of B is going to be equal to minus of beta 1 by beta 2 F B upon, that's it. So F prime of B is minus of beta 1 by beta 2 FB. So that's coming from the second equation. Okay. And now from the first equation you will get F prime of A is equal to minus of alpha 1 by alpha 2 Fa. Similarly, you can write the equations for G prime and G. Okay. So G prime at A and G prime at B are going to be expressions which are similar to this, because instead of F, I'm just going to replace it with a G. So that's what will happen. Again, decent amount of algebra. So that's what is written up here. F of B, I have used FB, but you can use F prime, whatever, doesn't matter. So either way, you have to just go ahead and substitute these in the earlier expression that we had. Okay, that I'm not going to do. It's all right there. Okay, so what are we finally saying? Finally, what we are saying is, I've got something like this. This is my operator, and I'm trying to show that this operator is a self-adjoint operator. Because that's my goal in all of this algebra that we are doing. So this, we then said that we are going to use the definition of this so-called self-adjoint business, and we said that operator operating on a function f and the inner product with g, and then this g comma f, this was our definition of the the self-adjoint operator. And then we said that this guy, now we did some amount of algebra and we showed that this is going to end up with something like this, which is this, which is f prime g, a to b, g prime f, b to a. Okay. So after that algebra, we came up here, and if we are able to show that this guy is equal to this guy, then it is a self-adjoint operation. Okay. And the story doesn't end here, because I've got these ends which are A and B, but then my conditions are given to me. So this is the condition that I'm going to have to satisfy. And when I'm going to try to satisfy that condition, I'm going to replace the f prime and the f prime at B, f prime at A, because this is f prime B. This is going to be f prime at B times G minus f prime at B times f prime at A times G at A, equal to whatever is the right hand side, which is going to be G prime at BF minus G prime at AF. And if you go ahead and plug these in, it is fairly straightforward to see that this is equal to this. Okay. All the algebra I am not doing, but you can see that algebra is done, and then you will indeed see that when you plug these guys into that, indeed you will see this is equal to this, which makes that a self-adjoint operator. Okay. All of this stuff we are doing just so that we can use the properties. Okay. We have not proved anything, and we are not going to prove anything also. And what we do possibly may not stand the rigor of a math proof or whatever, but we are just waving our hands decently and trying to make some conclusions. Okay. Okay. Now what we are saying is, if L is self-adjoint, there are infinitely many real distinct eigenvalues. And just like when we were looking at systems of equations, if you have got a real and distinct eigenvalues, the eigenfunctions are going to be orthogonal. Okay. So here also the same thing, we are just borrowing stuff from math. So eigenfunctions are orthogonal, and they form a set of basis functions. What are basis functions? Basis functions are functions which you claim are going to be the functions that are required for you to completely specify a particular function in terms of those functions. Those are basis functions. Okay. All right. And all of this happens under the umbrella, which is the orthogonality is not that straightforward here. It happens under the umbrella of that weight function, which is W. And the inner product is shown to be, or is defined to be, that number then. Okay. So all of this is something which we have done, kind of abstract, but what we are saying is all of this is going to be used by us. Okay, so that's why we have been kind of rapid in trying to show this, but we need to show it. We can't avoid showing that. So next thing is to see whether this whole business fits into what we have been talking about. All right. Okay, now we make a very bold statement here. I mean, not really bold because we have said everything. We say now that any function, okay, any function y is going to be a summation of some coefficient Cn times the eigenfunctions. Okay. Where have we seen this before? Any 2 pi periodic function we said was equal to a summation of sines and or cosines, right? Same thing we are doing here, but now this function, what is this function here? This is the solution to that differential equation, which is going to be in the Sturm-Liouville form. Okay, so this appears to be a much more general version of the so-called Fourier series. Okay, so I can take any function, represent it as a summation of these eigenfunctions, and can I evaluate these Cn's? Is it easy to evaluate the Cn's or difficult to evaluate the Cn's? It's fairly straightforward because these guys are orthogonal functions, which means that inner product of Fm, Fn is equal to 0 under the assumption of there being that weight function inside. Okay. So everybody is going to cancel off when you are going to try to get this Cn, and only one of these functions is going to survive. All right. One last thing is a periodic Sturm-Liouville system, which is Pa equal to Pb, Ya equal to Yb, and we'll show in just a little while that if you take a periodic Sturm-Liouville problem, then you are going to end up with the Fourier series. Okay, so the Fourier series is going to come out if we are talking about a periodic function. Okay. Now this is something which is, I'm not going to do the algebra, you can just look at it here. It says that any second order eigenvalue differential equation given as like this can be written in the Sturm-Liouville form. Any second order eigenvalue function like that. Okay. The reason why we are interested in all of this, remember, our functions so far which we have seen have been of the type Fm or F double prime was equal to some lambda times F, right? This was what we have seen in the two situations that we have seen. One situation was this, right? This was y equal to 0, y equal to L, and we said that these 2 points are anchored, and the other situation we saw was where at y equal to 0, f was equal to 0, and at y equal to L, there was an f prime that was given to me. Here at y equal to L, fL was given to me. And for both these situations, we ended up with an equation that looks like this. Okay? And this is nothing but the first equation, which is a general second order eigenvalue differential equation. So this is going to come to you as a home assignment. You are welcome to copy it, that's fine. But I want us to appreciate that this, okay, by the way, the next homework has been uploaded. So there is some deadline that has been given. So you need to submit. So now again, every week one homework is going to start showing up. Okay, so the Sturm-Liouville form, we are going to say that these equations which we have now are in the Sturm-Liouville form. So any of these equations can be reduced to this, but we will just be happy if we look at whatever we have. So this is the first equation that we look at. F double prime is equal to minus lambda square f. It doesn't matter whether the minus is there or not. The sign SIGN of lambda is going to change. That's all that's going to happen. Okay, so f double prime is equal to minus lambda f, and the first example that we saw was f0 is equal to 0 and fl is equal to 0. Okay, so you compare now with the standard Sturm-Liouville system. Sturm-Liouville system is written up there. Okay, so ddx of p ddx. So p, what is px? Suppose I would like to see whether this is amenable to that. What is p? What is q? What is q first? What is q? Q is right there. Okay, that is lambda on the right hand side. So which means q is not there, right? There is no term which has got a f on this left hand side. So q is going to be equal to 0. Okay, so this is the equation. Right? So f double prime is minus lambda f. So I have this negative sign, I can throw it there. This guy is equal to 0 for this particular example. And what is p of x? P of x is 1. So P of x is 1, Q of x is 0, W is equal to 1. Okay. This makes life a lot easier for us. Okay. So W equal to 1, and the boundary conditions were F0 equal to 0, which means here, what is alpha 1 therefore? Alpha 1 f0 plus alpha 2 f prime 0 equal to 0. What is alpha 1? If this is the condition, and this is what I am trying to mimic, so to speak, so this guy is equal to 1 and this guy is equal to 0, right? So this guy is gone and alpha 1 is equal to 1. Okay, so alpha 1 is equal to 1. Similarly, you can show beta 1 is equal to 1, alpha 2 is 0 and beta 2 is 0 because the gradient terms were not there. So this is in the Sturm-Liouville form. Now this is trivial, kind of, because we know that this ends up with sines and cosines, and anyway the orthogonality and everything was taken care of. So that's something that we knew already, but from the Sturm-Liouville system perspective, this is a system, this along with this is a system that is going to give me infinite eigenvalues and eigenfunctions which are orthogonal. That's the most important thing that we are looking for. Okay. Now let us go back to the last class. In the last class, we had this here. In the last class, we had f double prime equal to minus lambda square f or minus lambda f. Okay, and then we had f0 equal to 0 and f prime. So f0 was equal to 0, so which meant alpha 1 equal to 1, alpha 2 equal to 0, and then we had f prime at this, right, was equal to h of f. Okay, so which means f prime at L plus some h of f is equal to 0. So this is the second condition which I have, which is the beta 1 of f plus beta 2 of f prime. Okay, so this is also in the so-called Sturm-Liouville form, right? So if it is in the Sturm-Liouville form, now we have every business to say that the functions which we have got, which is the eigenfunctions, eigenvalues were km and kn, they are not integers, but still the eigenfunctions are orthogonal. Okay. So if the eigenfunctions are orthogonal, then now I don't need to look at this red stuff here. I can just simply say that I'm going to use this and I'm going to get this Bn like so. This is why we did all of this rubbish here. Okay. What we want to show is that if you are trying to get the solution to a differential equation using the separation of variables business, and you are ending up with a equation which has got a large number of eigenvalues, I am going to be able to use the summation, and the coefficients of the summations are easily obtained. That's why we have done all of this. Okay, and now there is no because nothing. We know that the eigenfunctions are orthogonal, period. We know that. Okay. Okay, so now let us go back here and look at another so-called interesting feature. Okay, so this is the Sturm-Liouville system, and in all of this, you can go through the algebra here. Now I'm not going to go through the algebra because this has been done in the past. Now that is a Sturm-Liouville system. We have just established that. There are different possibilities on lambda because we have to first get all the lambdas. Okay, so you have to get the lambdas, which means that I have to do the same stuff which we did in the past, which is lambda equal to 0, lambda equal to positive, lambda equal to negative, find out who are going to be the ones which are valid lambdas, which I can't throw out. Okay, so for this particular situation, we have done everything. So we'll just quickly go through this. We said that lambda equal to 0 comes up with a trivial value, so I'm not going to consider it. Lambda equal to minus k square, again it comes up with a trivial solution, no need to consider it. Lambda equal to plus k square, it's going to show up with the sines and cosines. and you are going to get n pi equal to kl, and that's the solution. So the eigenfunctions were this. What we are going to now show, or what we are going to see, which is something that the importance becomes apparent in 1 minute, is if we have this same system like this, but it is a periodic system. Okay, so which means that I'm considering a periodic Sturm Liouville system, and now it looks pretty trivial, but we will do this just for a reason. Now let us say that lambda is equal to 0. Suppose lambda equal to 0. What happens? What is f if lambda equal to 0? F double prime is equal to 0. Lambda equal to 0 means f double prime is 0, which means what is f? Linear. Yeah. So f is linear, and let us call it ax plus b. This is what we have done in the past also. Okay. But now it is periodic, which means that f at L is equal to f at minus L. Okay. That's one of the conditions for a periodic condition. So f at L is f at minus L. So f at L is AL plus B, which is equal to f at minus L, which is A minus L plus B. What can I say using this equation about A or B? Can I say anything? AL plus B is A minus L plus B. Can I cancel off the B? Yeah, because B is a constant, I can cancel off. This means A is equal to 0. You keep thinking this fellow keeps beating the dead dog all the time. We have already shown A is equal to 0 in the past. What about the second condition, which is f prime at L is equal to f prime at minus L? What is f prime? F prime is equal to A. And we are saying f prime at L is equal to f prime at minus L. What can I therefore say about A? A is 0. Always in the past it was a happy situation. A was 0, B was 0. So lambda equal to 0 had to be thrown out. In this particular case, A cannot be thrown out because this condition is indeed being satisfied here. We are saying that f of plus L was equal to f of minus L, so we could say that f is equal to A, correct? But when I do f prime of this comes out as 0. So f prime at L continues to be f prime at minus L. I cannot say anything about this constant A. The constant A has to remain inside. Okay, so this is one case where lambda equal to 0 is a valid eigenvalue. Lambda equal to 0 cannot be thrown out anymore. Okay. All right. So the next is, of course, lambda equal to minus k square. We have seen that it can be thrown out. And the other case is going to end up with sines and cosines. Okay. So this algebra we have done in the past. The only thing that was different here was to say that A does not go away, and you have now got sines and cosines. Okay, we stop here. I see you again next week.